discuss one more binary search tree, and this binary tree is usually called Treap. Sometimes it's referred as Cartesian tree. So it is basically the same structure, but when it's used as a binary search tree, it's usually referred as Treap. So what is Treap? Treap is basically just another method how to balance your binary search tree. So when we discussed last time, when you have a binary search tree, you need some mechanism to make the height of this tree logarithmic. And Treap is another method how to make this height logarithmic. So what operations can you make with Treap? It's a binary search tree, so you can make all the operations we discussed in previous lecture. You can insert element, remove element, find element, find the closest element, and so on. Find the next element, previous element, minimum element, maximum element. All the same operations as in all binary search trees. But to make the things more interesting, we will introduce two more operations. Operations split and merge. So how this operations works? Operation split makes the following. So in operation split, you have some parameter x, and it makes the following. You have a binary search tree, and you split this binary tree into two parts. So you make two binary trees. The first binary search tree contains all elements, let's say, less than x. And the second binary tree contains all the elements greater or equal to x. Like this. So basically, you have the ordered, some ordered set of elements. You like split this order in the middle and have ordered set here and ordered set here. Merge operation make the opposite operation. So you have two separate binary search trees. And in these two separate binary search trees, you need all elements of one binary search tree to be less than all elements in another binary search tree. You need all elements here be less than all elements here. And this operation just combines these two binary trees into one big binary tree. So basically, if you look on elements like elements in binary tree, just some elements in the sorted order, right? So here you have this set of elements sorted, and you just split this set of elements from here. So one part goes here, one part goes here. And here you have two sets of elements, one set and another set. So all elements here are to the left to all elements here. And you just combine all these elements into one big set of elements. Like this. Cool. Now, let's talk about structure of the tree. So how the tree is, what is the structure of the tree, and how do we maintain that the height of the tree is logarithmic? Very simple. Each node of the tree contains two keys. So let's print it here. So in each node of the binary search tree, we will have not one key but two keys. Let's say x and y. And we will maintain the following property. If you look on the left subtree, let's look on the left subtree. The first key of all elements in the left subtree is less than x. And the second key is less than y. And now if you look on the right subtree, the first key is greater than x, and the second key is less than y. That's all. That's the basic property of the trip. That's the only property we need to maintain. Now, why it is Cartesian tree, and what is the most visual way to show how this tree looks like? So if we look on like Cartesian plane, so we have y here and x here, and just use these two keys as coordinates on this plane. So if you have some node here, then all the left subtree must be in this part of the plane. So your left subtree must be here, and your right subtree must be in this part of the plane. So if you just put all the elements of the tree on a Cartesian plane, you will have some good picture which looks actually like a normal tree. So all elements in the left subtree are to the left and down, and all elements here are to the right and down. Well, let's build some content. Some tree. For example, you may have some element here, element here, element here, and here you might have something. Let's put it right here and here and here and here. Something like this. So that's the nice tree. Now each node has two values. So each node contains two values, x and y. Why you have two keys instead of one key? We will talk in a minute. Just wait a minute. Let's look on this key. So if we look on the first key, if we look only on this x key, then this tree is just a standard binary search tree. Yeah? So if you just ignore the second key, look on the first key, you will have a perfectly normal binary search tree, right? And if you look on the second key, you have something like a heap. So if you remember the heaps from the previous semester, in the not only binary heaps, in all heaps, like in binary heaps, in binomial heaps, in Fibonacci heaps, maybe you remember, we have this property. So the key contains the maximal element, and each child is less than its parent. So why it's called tree? Tree is actually come from two words. So it's tree plus heap. So it's basically the story behind this name. Good. So why we need this second key? Because I try to build a binary search tree. In binary search tree we have only one key. Yeah. So this x is the keys of your binary search tree. So, and the second key we will use to maintain the balancedness of the data structure. So we will just use this second key to balance our data structure. And how we will use this second key? Very simple way. We will assign second key in random. Just put random values in all keys. And I claim that if the second key is random, then the height of this tree is logarithmic. So if this is, then expected height is log n. So that's the plan. We need to build a binary search tree, right? So we have these x's as the keys we store in our binary search tree. Additionally, we will assign some random value to each key. Just pick some random value, and then we will build this tree using this property. And the fun fact is that if you make random keys, then the height of the tree will be logarithmic. So we only use these random keys to maintain the logarithmic height of this tree. That's the plan. Yes. So unlike the AVL tree, red bell-like trees, and other data structures which are deterministic binary search trees, this is random binary search tree. So this height is actually not determined. It is random, but with good probability it will be logarithmic. So if these keys are actually random, then with good probability this height will be logarithmic. That's the plan. We discussed in the previous semester, when we discussed randomized algorithms, we discussed that sometimes it's better to use randomized algorithms for various reasons. First of all, sometimes it's much easier to design randomized algorithms, and sometimes they're actually faster than deterministic algorithms. So that's one of the cases when it's actually I plan to write the whole code of this binary search tree on this board. So it is not deterministic, but it will be much easier to maintain this property, and the code will be much simpler. And it is I'm not sure. I think I will try slightly faster. I'm not sure. You can check this, but still, sometimes it's just better to use randomized data structures. Yeah. Let's prove this. So, why the height is logarithmic? No, for obvious reasons actually. Let's see. Imagine you have some set of elements in your binary search tree. So you have all these points, just some random points. This is X, this is Y. Let's see. The Cartesian, if all X coordinates and all Y coordinates are different, then it's only one way to construct the correct tree from these keys. So if all X's are different, all Y's are different, then there is only one way to construct the correct tree. Why is only one way? No, because let's see. What element should be the root of this tree? The root of this tree is always the element with the maximal possible Y. So if all Y's are different, we have only one maximum. So this element must be the root of our tree. Now, all elements to the left must belong to the left subtree. All elements to the right must belong to the right subtree. So again, we have no variability here, so there's only one way to build the tree, because we pick this element. If all elements are different, you have a unique maximum, so you pick this unique maximum as a root, and now you build the same in these two parts. So you build here, you take the maximal element, make it the root of this part, find maximum here, make it the root of this part. And now here again, you split all elements by X coordinates. So these elements must be the left subtree, these elements might be the right subtree. So this element must be here, this element must be here, this element must be here. For this part, this element must be here, this element must be here, here. Let's see this to the left. So this element must be here, here. So there's only one way to build the correct tree if all keys are different. Now let's see how let's see what about the height. What about the height? Let's see what is this root element. This root element is element with maximal value of I. So this element is maximal value of Y. But Y is random, so all elements get the same random value from the same set of random values with same probabilities. So because of the symmetry, all elements have the equal probability to be the root of the tree. So any element may be the root of the tree with equal probability. So basically what happens? We pick some random elements with equal probability from all elements. and make this random element the root of our tree. And now we recursively make the same thing for both halves. So we split all elements into halves, make the same recursive procedure here, make the same recursive procedure here. So basically it's the same procedure as in the quicksort. So if you remember how the quicksort works, it's done in the same way. We pick some random element, then split all elements into halves, like elements less than x, elements greater than x. And recursively make the same thing in both these halves. And by the same reasons like in the quicksort algorithm, the height of the tree, like the depth of the recursion in the quicksort algorithm, it will be logarithmic. So the height of the tree will be log n. Oh, expected. Again, how did we prove it when we discuss the quicksort algorithm? You may prove it like this. You have the whole set of elements. So let's pick the middle third of the elements. So with probability 1/3, you will pick one of the elements in this group. And if you pick one of the elements in this group, you will make two recursive calls. Each call is no more than 2/3 of n. So you will pick one of the elements in this group with probability 1/3. So it's basically every third time you pick one of the elements from this group. So every third time you split the elements in this way. So the total height is no more than 3 multiplied by log base 3 to 5, something like that. It's not very precise, but good enough. We need to reconstruct. No. We will not reconstruct the tree from scratch every time. We'll try to maintain this property after we add one element. So when we add one element, we will only reconstruct some part of this tree. Now, if you need to reconstruct the whole tree every time, it will be too much. That's not the point. It will work like in AVL tree. In AVL tree, you have some property, and you kind of need to maintain this property after you make some small changes. So you make some small changes, then you readjust something to maintain this property, and that's exactly what we'll do here. So after every small change, we will try to make some small changes in the structure of the tree to maintain this property. And again, I'll point to this. So this is the only property we need to care about. So we will only maintain this property. And if we maintain this property, then the height will be logarithmic. That's the plan. For what KF rating you need to use Treaps? No, we discussed last time. So in the modern competitive programming, it's not that popular to use some binary search trees but now. So it's a matter of fashion. So a few years ago, it was quite popular to use some Treaps and other binary search trees in the contests, but not now. Maybe it will be popular in a few years, who knows. Again, this course is not about competitive programming mostly. It's more about fundamental computer science topics. So binary search trees are fundamental data structure for the algorithms theory. So it's widely used in all various different, very complicated data structures. So basically, what you do with the binary search tree, you have some set of elements and you maintain this set in the sorted order. So you can insert, remove, find elements and so on, or you can do all these operations in log n time. That's a very fundamental result, that you can maintain the sorted order of the elements and make all the operations in log n time. And obviously you cannot do it faster, like we discussed tomorrow in the home task discussion. Okay, that's all. You stop posting that everything is clear. You can start to you can continue to post that everything is clear every 30 seconds. It was quite helpful for me. So that's the whole plan. That's the whole plan. We will build a binary search tree, assign random second key, and maintain this property. That's the whole plan. Cool. Now, how to make the operations. I will start with these two operations. So first I will explain how to implement these two operations, and then I will explain how to implement all the basic operations like add element and remove element. That's the plan. So let's first explore these two operations. So first, how to split the tree. Let's see. Let's I need some more space here. I plan to put all the code and picture in this part of the board. Let's try if I can do it. First, the most important thing is a picture. So this data structure is very visual. You can write a picture like this and see what's going on. So how to make split? Let's see. You have this subtree. You have this subtree, and you need to split this subtree by the value x. So you have the sound value x, and you need to split the subtree in two parts. First part is elements less than x. Second part is elements greater than x. Let's look on the root of this tree. So this root should belong to one of the parts of the tree, and it's easy to see to which part should belong. So if this root is less than x, then this root should belong to the left part of this tree. If the root is greater than x, then it should belong to the right subtree. Cool. So, for example, if this root belongs to the left part, so if the key in the root is less than x, then let's see. Let's look on both subtrees of this tree. So this tree have left subtree and the right subtree. In this left subtree, all elements are less than x. So if the root is less than x, then all elements here are also less than x. So all elements here must belong to this left part of the splitted tree. And in the right subtree, some elements are less than x, some elements are greater than x. So let's recursively go to the right subtree and split this right subtree into two trees. So we'll recursively go here, split this tree into two trees. Now, these elements are less than x. These elements are greater or equal than x. And now all we need is to put this left part as a right child of this this root. So we'll just put this left part here. That's all. And now we have two trees. This is the first tree. These are all elements less than x. So all elements less than x are the left subtree, the root, and the left part of the splitted right subtree. And all elements greater than x are just the splitted part of the right subtree. So that's all. How I will implement this? I will implement this the following way. So I will make split. I need a letter for this root. I already used x. It's always complicated. So let's call it node. Node by x. So this will be a recursive function. It gets the node which corresponds to this subtree, and it splits this subtree into two parts, elements less than x, element greater than x, and returns two roots of these trees. So when we return from this function, we will return these two roots. We will return this root and this root. No, root of the tree is basically how do you, when you need to get the tree, you basically need to get the root of this tree, right? So root is something describes the whole subtree below this root. So this split receives a root of the tree it needs to split, and it returns two roots of the two trees after you split this tree into two parts. Makes sense. Well, let's just implement this. So, just like in this picture. So we look on this root. Look on the key in this root. If this key is less than x. No, first we need to stop the recursion at some point. So if this node is null, if the tree is empty, that's important. We need to split the empty tree into two empty subtrees. Yeah. Null and null. So that's the case when the current tree is empty. If you have empty tree, you need to split empty tree. You split it in two empty trees. Makes sense. Now, if it's not empty, let's look on the root of it. So if it is less than x, then it belongs to the left subtree. We need to split the right subtree into two parts. So let's say p equal to split node right by x. So we split this right subtree into two parts. Now this split returns you two roots of this subtree. So it returns you these two roots, this root and this root. Now we need to take this first root and place it as the right child of node. Right? And that's all. Now we just return two roots of the constructed tree. So first root is node, second root is the second part of this split of the right subtree. So just return boom, node and p second. That's all. So that's the whole code of this case. So if this node belongs to the left subtree, we take this node, take its right subtree, recursively split this right subtree into two parts, put this as a right child, and return these two roots. Did you miss the first part? So this is the property we need to maintain. So let me again. This is the property we need to maintain. I will use the split operation later. I will use it. I promise. I didn't say why I need these operations. I will need these operations. Okay. Now, if not, let me just finish this code. So if node belongs to the right subtree here, we do the same thing, but in mirrored. So I will not draw the same picture. So we just imagine the same picture mirrored horizontally. Yeah. So we just split the left subtree. Now we put as the left child the second tree from this left subtree and return the pair of first and node. That's all. That's the whole code of this split operation. Now the merge operation. In merge operation, I need two trees. So I have one tree and another tree. Let's say I have tree A and B. So how to merge those two trees? Let's see. So let's see which of these two nodes will be the root of the merged tree. So the root of the tree is always the element of the maximal y. So element of maximal y is one of the roots of this tree. So let's look on the root of these two trees. Check which root have the maximal value of y. This element must be the root of this merged tree. For example, if y coordinate of this a is greater than y coordinate of this b, then this root will be the root of the whole tree. Now let's see, it has two subtrees. So this element will be the root of the tree. And now we need to put all these elements must be in the left subtree. So we just don't change this. And all these elements must be in the right subtree. So we need to put all these elements in a single tree and put this merged tree as the right subtree. So we do it recursively. We just call recursively the same procedure for these two trees. So we call for these two trees, merge them into one big tree, and put this tree as the right child of this A. That's all. That's the whole picture of what's going on. So this A is the root, left child is the same, right child is the merge, right child plus B. Let's go. Merge A and B. Well, first again we need to check if the tree is empty. So if A is empty, we just return B. If B is empty, we just return A. Now both trees are not empty. So let's check which tree have the minimal or maximal value of y. So if AY is greater than BY, then this A will be the root of the new tree. So what we do, we just take the right subtree of A, merge it with B, and put this merged tree as the right child of A. Let me write it in one line. So I right will be merge of A right and B, like this. It's merge. Not bad, okay. That's all. Return A. Again, like here, when you merge two trees, you return the root of the new tree, right? Else you have the same thing. If B is the root of new, then you merge A and the left subtree of B. That's all. That's the whole code of these operations. Like I mentioned, the code of this of the tree is one of the simplest of all binary search trees. Cool. Let's talk about asymptotics. Now, if we believe that the expected height is logarithmic, let's prove that time complexity of both these operations is linear by the height of the tree. Now let's look here in this split operation. So we have a recursive split operation. So we have this split of node and x. And here we have recursive calls, and each recursive call here and here by x. In both the recursive calls, we go to one of the subtrees of node. So each time we go deeper in the binary search tree. So if the height is logarithmic, then the number of recursive calls will be log n, obviously. Here we have the same thing. So here we have A and B. And here we have two recursive calls. One recursive call, two recursive calls. In both recursive calls, we go deeper in one of these trees. So we either go deeper in the tree A or we go deeper in the tree B. So the total height of this tree will be decreased by 1. So each time we go in one subtree one step deeper, or we go in another subtree one step deeper. So total time we can go deeper in the subtree is up to 2 log n, because we may have at most log n steps like this and at most log n steps like this. So the total number of recursive calls will be up to 2 log n. So the time complexity here is also logarithmic. That's all. Now, let's move to other operations. So let's see how to add elements or how to remove elements. Oh, hi. We're discussing Treaps. So how to add new element? How to add new element into Treap? There are two ways. One way is easy to implement, but it will be a little bit slower in the real world. But what you can do, just using these operations, you can take your binary search tree, then split it by x. So you have one element less than x, and here you have elements greater than x. Then you make one small tree of one element, contains only x. And then you make two merge operations. And you have the same tree which contains all elements of your previous tree plus x. Yeah? So you split it by x, put this x in the middle, then make merge, and you have the whole tree contains all elements plus element x. That's one of the simplest implementation of the additional elements. But it is little bit. No, how can you remove elements? So when you need to remove elements, you can do it in the opposite order. So you have this element, you can make two splits, split by x and split, let's say, by x minus 1. So you have all elements less than x, then you have this x, elements greater than x, and then you make one merge. So just remove this element, make merge of these two trees, and have this element. Why you can use this tree is a binary search. You can use any type of the binary search trees. We just discuss various different strategies how can you build a balanced binary search tree. So Treap is one of the way to construct a balanced binary search tree. I just explained this because it's much easier to show how to make split and merge operations in the tree. Because if you can make split and merge operations in other binary search trees, in deterministic binary search trees. I'm not sure about AVL trees, but you can do splits and merges, and in the red-black trees, you can do it in 2-3 trees, in B trees, in various different trees. But Treap is like the easiest way to explain that it's possible. It's possible to make split and merge operations. Yeah. That's why I use trees. It's only for educational purpose, basically. In the real systems, you most probably will use something like red-black trees or something like that. That's true. Let me go back here. So this is possible. You can just use these operations, but it's it's a little bit too slow, so you kind of make 3 operations instead of 1. That's easier way to make addition and removal of elements. So when you need to add new element, what you can do actually, let's say node x, is just to make the following. So let's check if this x is the, so what element will be the root of the new tree if you have this tree and plus 1 element. So what element will be the root of the new tree? It will be either the root of this tree or this new element. So let's check what element have bigger value of y. So if I need y, so I need x and y. I need to generate this y before I start this recursion. So let's say if this y is bigger than node y, then this new node is the new root of the tree. So you have this node plus this element. So this element is the new root of the tree. So how to add this new root to your tree? You just split your tree into 2 parts and put them as the children of your node. So just make p split your node by x and just say, I don't like this. I need something to call this new node. New node. That's better. I'm not very creative, okay, in naming. So if this new node, so we make this, so we just split our tree by node, new node x. And just put these 2 subtrees as the children of this new node. And return new node. Like before, we return the new root of the tree. And if not, we just put this new node in one of the subtrees of ours. So if new node x is less than node x, okay, not perfect. So then we add this new node in the left subtree. Just say node left equal to add node left. I just love one letter in the identifiers. Yeah. New node, and else you do the same for the right child and so on. Time to try it. You need the same line to add new element to right child. So basically, you can make one additional recursive function which adds new element into your in your tree. And instead of calling 3 different functions, you should call split, then merge, you just call one function, it will be like 3 times faster. Okay. Good? Good enough, right? Again, you stop to say everything is clear. That's... Now, what I want to talk about. Okay, let's move to something new. What I want to do next is a little bit different. I want to build another data structure based on binary search trees. So I want to do the following data structure. Let's see. I want to do data structure which maintains some lists of objects. So let's have, so the basic the basic object of this structure is just list of some objects. Let's say you have some objects Q, Y, P. I'm better like this. K, C, W, N. So I just name all the objects of different letters. Okay. So we have a list of some 7 objects. And I want to do the following operations. First operation is to combine 2 lists into one big list. So this operation works. So I have one list of elements plus another list of elements. And I want to combine these 2 lists into one big list of elements. Very simple operation. Let's call this list like A and B. So I have list A and list B. And I want to be able to combine these 2 lists into one big list. And second operation is split, obviously. So I have one big list. And I want to split this list into 2 big into 2 smaller lists. Like this. So where to split? I want to have, for example, I want to split taking the first k elements. So by k. Also, so let's split list A by k. So k is the size of this first list. So I have this list A. I want to take first k elements of this list and put them in one list, and all other elements put in the second list. And also I want to work the get element by the key. So I just want to be able to pick the element by the index. Good enough. Yeah, good enough. So that's all. That's operations you want to have. You want to have some number of lists, and you want to change this list. So you want to be able to merge 2 lists, like concatenate 2 lists into one big list. You want to be able to split the list in the middle and get 2 separate lists. And you want to be able to get any element of these lists by its index. That's all. Let's have another example. So let's split this into half. That's plus something, the A, and something like B. So I have 2 lists. So when I make this merge operation, I get this big list. Then I call something like split by, let's say, 5. And I have these 2 lists. Good. So how we make both these operations using binary search trees? How you make an expression using binary search trees? That's simple. We will maintain these lists as binary search trees. That's the plan. So in these binary search trees, we have split and merge operations. So we will maintain all these lists as binary search trees. And when we need to make merge, we merge these trees. when we make split, we split these trees. But in binary search trees, you need to have keys of your elements, right? So we'll just use the indices of the elements as the key of the binary search tree. So here we have keys like 1, 2, 3, 4. Here we have elements like 1, 2, 3. Now, what happens when you need to merge two lists into one list? You only can merge two trees, then all keys of these elements are greater than all keys of these elements. So how to make all these keys greater than all keys here? No, you can use mass operations and lazy propagations like in segment trees. Yeah. So you can just make a lazy operation in the root of this tree. Just increase all the keys by 4. So you take all these keys, increase them by 4 using lazy propagation. Then you have the keys 5, 6, and 7. And now all the keys in this subtree, in this tree, are greater than all the keys in this tree. So you call this merge operation and merge these two trees into one tree. And how to make split operation? You just split. You take this binary search tree, split it by the key k. So you take first k elements here, all elements key. Now you have here you have keys 1, 2, 3, 4, 5. Here you have 6 and 7. And now you make -5 to all these keys again as mass operation using lazy propagation. And you have keys 1 and 2 here. That's one of the possible ways how to implement this. So again, you take some binary search tree. For example, you can take these Treaps or any other binary search tree which can merge and split these trees. Then you use lazy propagation to change the values of the keys. You can do it. Why not? Just put the operation +4 in the root of the tree, then use lazy propagation to change all the keys below. And now you change all these keys. You can merge these two trees into one big tree because all keys here are greater than all keys here. So you merge these two trees using this merge operation and get this. But it turns out you can do it like this, but it is overkill. You can do it much simpler. So how to make this without all these mass operations, lazy propagation and stuff? You can implement the same operations without any keys. So if we know that the key of the element equal to its position in the list, we just don't need to store all these keys because the key is always equal to the index of the element. So we will just ignore all the keys. We'll just ignore them. The index of element is defined by its position in the tree, right? So, no, again, how the binary search tree works. Binary search tree contains some set of elements, and these elements are sorted by the key. Here we have some elements, but these elements sorted not by the keys. We don't have any keys. We just sort them by the position in this list. So what I want to build? I want to build a binary tree which contains these 4 elements in this order. That's the plan. Well, for example, let's say we have element. Let's put some. We still need some second keys. So let's say. So this is key y. We need some y's. So let's say we have 2, 5, 8, 1, 6, 2, 4. I have 2 keys for. Let's make all keys different, just for simplicity. You actually don't need to make all keys different all the time, but if you have a big range of y's, if sometimes you have equal y key, it's not a big problem. If you have a lot of equal keys, that may be a problem. You have like list of elements with the same key, but yeah, good enough. So now we just built the tree of these elements using these y keys. So when we use y key, so the root of the tree is the key with maximal y. So p is the root. The y of this is 8. So this is the y key. Yeah. So in the left subtree we have this y. So we have 5 here, and here we have q. Q has 2. And in the right subtree we have this k with q1. That's all. This tree describes this list. Again, if you look on this tree and just iterate over all elements from left to right, you have element q, then y, then p, then k. That's exactly the order of the elements in this list. And for the second tree, you have this element w, here we have element b, here we have element n, 6, 3, and 4. And this tree describes this list. So again, if you go from left to right, you have w, then n, then b. That's all. Now, what happens when you want to merge these two trees? So you merge. Sorry. So you merge trees. Again, each tree is specified by the root of this tree. So you pick these two roots and call the merge operation of these two roots. So you merge p and w. What happens when you merge two trees? You look on the roots of these trees and look which tree should be the which element should be the root of this big tree. Why w is the root? Because y is bigger. I just built the standard tree. So this key specifies the height of this tree, or of the not the y coordinate. I try to build the correct tree. So I just pick the element of maximal y as the root. So when I try to merge these two trees, I look on these two roots. Just check which element must be the root of the new tree. Element p has bigger value y, so this element must be the root of the tree. So now I take this element as a root, and now I need to merge the right subtree of this element and w. Yeah. So again, so I have these two elements. This element is the root. So now I want to take these two elements, merge them, and put the combined tree as the right child of p. So I call merge from k and w. Now again, I look on these two elements, see what element should be the root. W should be the root of this. So I take this element as the root and try to combine the left child of w and k. So I merge k and the left child of w. Left child of w is not null. Now I want to return from this. So when I want to merge something and null, I return this something. Yeah. So I return k from this recursion. Now I take this merge tree and put it as the left child of this W. So put this K as the left child of W. And return this W as the root of this merged tree. And now I put this merged tree as right child of this P. So the right child of this P will be W. That's all. That's how we merge two trees. You actually don't need this key X when you merge two trees, right? So when you merge trees, you know that the structure of trees determine the order of the elements. So you actually don't need any keys. Just look on these Y values to make everything balanced, but you don't need this key X. Cool. And now we have this merged tree. This merged tree defines this list. Again, in this list you have elements Q, then Y, then P, then K, then W, and B. Right here. And how you make split operations? To make these split operations, you actually need to find where to split. So you need to find this position of the first 5 elements. To find this position, we will pre-calculate the size of each tree. So Y is the size of this tree. 1 of this tree is 2. Here is 1. Here is 1, 2. 4 here. And 7 here. So I will pre-calculate for each element the size of this tree, the number of elements. Now, how to make split? So again, I call split in the root in P by the first 5 elements. So I want to take this root and split the first 5 elements of this root. 5. It's too easy. Let's make it 6. And it's still easy. Let's split by 4. Yeah. I want to add one more. Let's add one more element here. So let's see something here. Which letter we don't use? Let's say L. Just small adjustments. No, you can use X as the index of this of the elements, but actually you don't need to store all these X's. That's what I mean. In this data structure, we don't use the first key of this elements, the main key of your binary search tree, because the order of elements is defined not by these keys, but just by position of the element in this binary search tree. So the position of the element defines its index. That's the idea. So we actually don't need these keys anymore. Can positions we use the key change after we merge? I don't get it. When you I explained it here. So when you merge the trees, the indices of this element will be increased by the same value. You can do it, but you don't need to do it. You can just make your merge operations without any keys, and the positions of these elements will be correct positions. So the position of this element will be equal to index of this element. That's what I want to do. So I'll just I need all these X keys in all nodes. Just don't have these X keys. I don't need them anymore. What I was talking about? What I was talking about? Yeah, I want to take this tree and split it by the first 4 elements. So I want to take this tree and cut first 4 elements of this tree. So I want to cut this Q, Y, P, and K from this element. So I need to form one tree of these elements and another tree of these 4 elements. I want to split it here by 4. That's the plan. Just small fix. So I take this list, split it here, and make these 2 lists. Let me adjust the sizes. So this is 1 now, this is 2, this is 5, this is 8. Nice. Let's use this. So I start from the root, and I want to cut first 4 elements of this tree. Let's look on this root. Let's see in which part of this splitted list will be this root element. So how to see where we will build root element? So this root element will be after first 2 elements. We have 2 elements in the left subtree. Then we have our root. So our root have index equal to 3. Yeah? So we have first 2 elements here. So index of this element is 3. And I want to cut first 4 elements. So this P should belong to the left part of this splitted tree. So I take this P, put it in the left part, and then I need to cut this W into 2 halves, such that first half contains 1 more element. So again, I want to split this tree, taking the first 4 elements. So I take this whole left subtree, 2 elements here, plus these elements, 3 elements. So I need 1 more element from the right subtree. So I go to the right subtree and try to cut first 1 element from this subtree. So from here I call split of W, cutting the first element of this subtree. I go here, try to cut 1 element from this tree. How to cut 1 element from this tree? Well, let's look on the index of the first element. So index of this W will be again 2 plus 1, it will be 3. So this W should belong to the right tree. So I put this to the right tree and then go to the left subtree and try to cut 1 element from this left subtree. So from here I go to K and try to cut 1 element from this left subtree. Now again, I look on the position of K. K has index 1 because left subtree is empty. So K is index 1. So when I need to cut 1 element, I just take this K and cut 0 elements from M. You can just return this left subtree, but I will just, for simplicity, I will call it like this. Well, now it's simple. You just from here you just return. You return 2 trees. First tree is empty. Second tree contains M. Now again, for this K, you need to take first element K. Take this null as the right subtree. So the right subtree of K is now this null. And return these 2 trees as a result. So from here you return left subtree is K, right subtree is M. Again, you have list K and M. You try to split it, taking the first 1 element. So now you have one list contains K, another contains M. That's what you do. This one is the second list. Now you go back here no, back here. So you take this W, connect the right subtree as the left subtree of this W. So you connect this M as the left subtree to this W instead of K. And now you have two subtrees. First subtree is this K, and second subtree is this W. So this K contains the first element. I need to cut first element from this subtree. So I take this subtree K and this subtree W. This contains one element, this contains all other elements. I return K and W. And now I connect this K as the left child of P, a right child of P. Like this. That's all. Now, again, in this P, I had three elements. I cut one element from this subtree, put it as a right child. So now in this tree, I have four elements. That's what I want. I want to cut four elements from this P. So now I take these three elements plus this one. So now I have four elements here. So that's all. So now in the end, I have this tree contains the left part of this list. This tree contains the right part of this list. Makes sense. That's all. And now when you have structure like this, you can perform some strange operation with the list. So what you can do? For example, you have some list. You have some list of elements. You can split it here, make this three lists. So first list, second list, third list. Then take this third list, put it in the end. Let's A, B, and C. And merge them in different order. So you can take all elements in A, then elements in C, and then in the end take all elements in B. So you can cut some segment of your elements and merge it in the end of the same array. So take it from here, merge this A and C, and merge the result with B. So you have this segment will be moved to the end of your array. And you can do all these operations in log n time. So each of these operations works in log n time. So you make these two splits plus one merge, two merges. And so on. You can perform, you can make some segment operations again, like before. When you have a segment tree, you can perform any segment operation, like in segment tree. So you can rearrange all these elements and then calculate sum on some segment, or rearrange some elements and add something to the whole segment, and so on. So you can make all the same operations like in binary, like in segment trees, but also you can rearrange the elements using these splits and merges and so on. And that's fun. Should we talk about persistent data structures? Let's just mention that you can do all these operations using persistent trees. And actually with Treaps it's very easy. So if you need some persistent Treaps, you just make all the same procedures. The code will be the same, but every time instead of changing something in the element, you just create the new version of this element. For example, let's make, just remove everything not necessary. So, for example, you have this list and you want to insert another element here. So you want before this K, you want to insert another element, let's say B. So you want this B to be before this K. So what you do, you want to connect this B as the left child of K, but you don't want to change this K. So you just copy this K to another node and make this B the left child of this new node. And now you want to connect this K as the right child of P, so you just copy this P put it as the right child of this new copy and connect this left child as left child. And now you have two versions. This is version 1 without B. This is version 2 with this B. And so on. So it's very simple to change all the code. I already erased it, but you can do it by yourself. Every time you need to change something in your node, to change some of the children, to change the value and so on, you just copy your node and return this copy as a result of your function. It's very, very simple, and you can do it all these operations in persistent way. I want to talk about problems with persistent trees. Maybe we'll discuss them in the next home task. But sometimes you need something like this. It's not very often, but sometimes you do. Any more questions? That's basically all I tried to discuss today.